this week we'll be continuing with some applications of group action. So first I will do a quick review of all the contents we covered last week. So last week first we started off with relating geometric symmetry to abstract symmetry. We went over this by considering automorphisms, and from that we defined something called as group operation. So when we had some operation where a group operates on some set which gives some result in some set. I should check. So I hope everything is audible. I should have asked that. Yeah. So after that, uh, we also saw that a permutation map, and then basically when we have a permutation map, we saw that under group action we have something called as an orbit. Orbit is where if we take some element S from the set, where the set travels under the group operation or group action is called as the orbit of that element. And then we have similarly we have something called as the stabilizer here. Stabilizer is a subgroup of the group where it is the elements which when operates on the set element does not change the set element. It forms a subgroup. And then we also covered equivalence class. This was not covered in Artin, but I covered it. So we also established how equivalence class is basically similar to exactly same as an orbit, and how they both uh, form a partition of the set. And then we went to a very important theorem, that is the orbit stabilizer theorem. Orbit stabilizer theorem, which is also called as the counting formula. And then we saw an example of using a dodecahedron using the orbit formula, and we counted that it has 60 rotations. We finally ended off with saying that there is a bijective correspondence between all the group operations of G acting on S, and between the homomorphisms G to the permutation of S, which is defined as this map, the permutation map, which here. There is the bijective correspondence between these both. That the homomorphism itself may not be a bijection, to be clear. So we ended up with that. And in this lecture, I said that first I will start by covering an example related to the bijective correspondence, and then we will go off further with the next topic. So first, this is example 8.5. 8.3 and 8.4 I will not be covering in the lectures. So in the example we are trying to see that the group of automorphisms of the cyclic group of order P is isomorphic to the multiplicative group f of P, that is the finite field of non-zero elements from the finite field. So we take f of P itself to be the cyclic group under the addition operation, so which is generated by 1, and then we take the multiplicative group to be G. So G will act on the additive group by left multiplication. So when we have this left multiplication, so G is the group which is the multiplicative group, and then the set we have under consideration is the additive group. So this if we take the map from G to the permutation, G is the multiplicative group. From the multiplicative group to the set, then we have an injective homomorphism map, because trivially it goes through all the elements. So when we have the permutation map that goes under G, yeah, we have a permutation map. So the automorphism is a subgroup of the permutation. So permutations, there will be many maps under the permutation. So which is the bijective correspondence defined here. So under this map, we have also the automorphism map. all the maps we have may not be an automorphism, as I showed in a very first example here. So in this example, we have only two automorphisms. The other one was going only to the identity. The homomorphism was going to the identity. So not all of them will be an automorphism. So next, we establish that it is an injective map. So next we have to establish that it is surjective. So the permutation map is bijective, and if we take one permutation map, uh, it will the permutation map we have taken will be also in one of the automorphism. So when we take that, since the permutation is bijective, then that map is surjective. So we can fix this by sending the identity 1 of the uh, additive group to any other non-zero member. So in that sense, the homomorphism is also bijective, since we have established both injectivity and surjectivity. So this is one example. So there are two other examples which are similar to this, which uses the bijective correspondence between the action and the homomorphism. I should check. So then next topic we are going to look at is finite subgroups of the rotation group. So before I get started, I will recall some facts. So if you have an n cross n matrix, it is an orthogonal matrix if A transpose A gives us the identity matrix. So if we take any orthogonal matrix, it has determinant +1 or -1. So these orthogonal matrices form a subgroup which we denote as O subscript n, that is orthogonal group of general linear group. So general linear group consists of n cross n real matrices which are invertible. A subgroup of them form the orthogonal group. The conditions of the orthogonal group is that A transpose A gives us the identity map. So another subgroup of this is called as special orthogonal group, such that the determinant of A is 1. So for orthogonal group, the determinant can be plus or minus 1. For special orthogonal group, it should be 1. So that this is. So now there is a nice theorem where we say that every finite subgroup of G of special orthogonal group of subscript. Yes, it is a special linear group. Yeah. So the theorem under what we want to see is that if we have SO3, every finite subgroup G is of five forms here. We have either the cyclic group of rotations about a line, the dihedral group, the tetrahedral group, the octahedral group, and icosahedral group. So I have used the image from Artin, which shows not all of them. Tetrahedral, the octahedral group is either a cube or the octahedron. The rotations of a cube or octahedron. Icosahedral group is the rotations of dodecahedron or icosahedron. The rotations of dodecahedron was discussed in the previous lecture, and it has 60 rotations. I'm not going to derive the number of rotations of octahedron or tetrahedron. We will be deriving them in a different manner from the previous lecture in this theorem. So this is a bit of a long theorem, so it has many steps under that. So first, we take G to be a finite subgroup of SO3. So let G be of order n, then every G we have except the identity is some rotation about a line L. So if we have, so if it goes through this is a unit sphere. We have taken a unit sphere in R3. So if we take a line L, then G will be some rotation about this. G will be some rotation about this. So if we take rotate G, then the line L itself will pass through 2 points. We have the line L. This will pass through 2 points here. We can call them as two poles, P and P dash. So the line G does a rotation, and it passes through two poles. We call them as P and P dash. G does a rotation along line L. So any rotation we take can be considered of this particular form of rotation. So we call them as poles. Next, whenever we have any group element G operate on a pole, then it will give us some other pole. So for example, in this image, this is a tetrahedron, so it has so if we have, this is one pole. If we have an operation G on here, it will go to here. The next, it will go from one pole. This is one pole. It will go to the next pole. It will not stay in somewhere in between, because then it will not. If it stays somewhere in between, then it will not preserve the shape of the tetrahedron. So whenever we have such an operation, orientation preserving rotation, then it will always go from one pole to the other pole. So that is what this line means to say. So now if we take capital P to denote all poles, so all the poles are basically points which are vertices, all the vertices, center of the faces. So that there will be a line through vertex, and here center of the faces, and edges, center of the edges. So these are all these will constitute a pole. So it is very easy to see that if when G acts on the capital P, that is the set of poles, then it is a valid group action. So to prove that it is a valid group action, we have to just show that if we have some XP, then if any other group member acts on this XP, then it is also a pole. So this element XG X inverse will fix XP. So this is a valid action. GP goes to P, so it is a valid group action. We also can verify both the rules needed for a group action. So in this way, we can see that if a set of rotations, G is a group of rotations which acts on P, then it is indeed a valid group action. About all the subgroups, we need to now look at the poles in the group. So the identity will not move anywhere, so we will not have so excluding identity. So if we have there are the order of the group is G, so each group element will have one rotation. So order of G is N. Each group element will have two rotations, so 2 times n minus 2, but it is not correct to assume that, because a same pole, like for example, if I take here, not here, so for example, if I take a square, it is possible that a pole can be shared by two different group actions. I don't know where to show that. I will show that later. So it is possible that a, a single pole can be shared by multiple actions. So I will show that in a different picture. Can't draw a dodecahedron here. So So first we will start with the pole P is a set and group G acts on it. So when we have a set group action, then we will also have its own orbits and stabilizers. So when we take a stabilizer of a pole P, the stabilizer is basically all the rotations along the line 0 to P. So we have this line here. So all the actions along this line. So it along this unit sphere, it can also inscribe a dodecahedron or a icosahedron, so anything. But all the actions which uh, through that line, through this point P dash, so all those actions, the group elements which can cause those actions belong to the stabilizer. So the stabilizer is a cyclic group because it is generated. So if the cyclic group is generated by the smallest angle theta, which is given by 2 pi r over rp. So since it is a pole, rp will at least contain two elements. So next is from the orbit stabilizer theorem. So this is the statement of orbit stabilizer theorem. The order of the group is equal to the product of order of the orbit. This is the orbit and this is the stabilizer. So it is product of both of these. So order of the stabilizer is Rp, since we have established that notation here, and order of the orbit is Np. Np is basically number of poles in the orbit. So if we have one orbit, it can travel to multiple other orbits. So all the orbits it can travel. So they are considered the equivalence class of that orbit. So if we take one pole P, a given pole point P, then it will have uh, Rp minus one group elements. So Rp is the order of the stabilizer minus the identity. So one pole P it can travel that. So if we can take that for all the poles, then we will have this relation. So we are here we have minus 2 because we are excluding the identity of the overall rotation, and here we have rp minus 1 because for each pole we are identifying the pole's identity. So we have taken all the poles here. So uh, if we have two elements in the same orbit, we know that their orbits are same because they belong to the same equivalence class. Then the order of their stabilizer are also same. The stabilizer may not be same, but their orders are same. So if we have np poles in orbit, then uh, this is for one pole. So if we have np poles, then together we have np into rp minus 1. So if we have, since the group is finite, the number of orbits will also be finite. So we have this relation from the this is for one orbit. So if we have like k orbits 1 to k, 1 to k, then we will have I is equal to 1 to k, this relation. So n times r is one capital N, because from the orbit stabilizer theorem we get the capital N, and then finally we get this is here we get capital N minus small n is equal to 2. So we divide both the sides by the capital N, that is the order of the bigger group. Then we finally get this relation, that is 2 minus 2 by n is the sum of 1 minus 1 by ri. So here I have claimed that this gives us that there can only be at most 3 orbits. Why I make this claim is that this side is uh, less than 2. This side is at most 2, and each term here is at least half, 1 by 2. So if we have 1 by 2 plus 1 by 2 plus is 4, this should be strictly less than 2. So this side is strictly less than 2, and this side can we can have at most 3 orbits. So this is like at least 1 by 2. The each term will constitute at least 1 by 2. So we can only have at most 3 orbits. So if we, what if the number of orbit is 1? Then we have 2 minus 2 by n is equal to 1 by r. This is impossible because this term is at least greater than 1 and at most 2. But this term is varying only between 1 by 2 and less than 1. So this relation is not possible. If the number of orbit is 2, we have this relation. So uh, from the summation, if we take everything, we can simplify this relation to 2 by n is equal to 1 by r1 plus 1 by r2. So r1 and r2 are the order of the stabilizer as defined here. So they are the here, yeah, here. They are the order of the stabilizer. Uh, the stabilizer R1 and R2. So what we have to get is that both the sides should be equal. So this is only possible if R1 R2 is equal to n. So when R1 R2 are equal to n, then the order of the orbit is 1 by the orbit stabilizer theorem. So then this is what we get is the cyclic group uh, of rotations along a line. So if we take cyclic group of rotations, so probably insert a yeah. Yeah, so this is basically the cyclic group. So we have the cyclic group. This pentagon is embedded in the unit sphere, and a line L will pass through the center of the pentagon perpendicular to it. So this is basically rotations, 2 pi by 5 rotations along it. And if we take this line L and the unit sphere, the line L will touch 2 points. That is on one side over there and other side over here. So that is one side over there and other side over here. So it is basically uh, 2 poles, and these 2 poles are fixed by the entire unit sphere. That we can see that it is 1. So we have actually gotten our first class of the five items. So we have gotten CK, the cyclic group of rotations. So next is we have verified cases 1 and 2. 1 is not possible when the order of the orbit number of orbits is 2. We have the cyclic group, and if we have number of orbits 3, so we have this is the main relation which we simplify to this. So each Ri, again we have to apply constraints here. If each Ri is at least 3, so this is 1 by 3, 1 by 3, 1 by 3, then that is 0. So if it is greater than 3, uh, then this entire term will be negative. So that is not possible. So at least one of these terms must be 2. So we assume R1 to be 2. So if we have R1 to be 2, in case 1 we assume R2 to also be 2. So if we get 1 by 2 plus 1 by 2 is 1, 1 minus 1 is 0. So we get this relation. 2 by n is equal to 1 by R3. So if R3 is equal to 2, then we have n is equal to 2 by r. So we now have to fix r value. So if R3 is equal to 2, then we have 2 poles. These 2 poles make the orbit O3. O3 is the orthogonal group of O3 is basically 1, 0, 0, cos theta minus sine theta, sine theta, and cos theta. Yeah. So this gives us one. So orthogonal group O3. So every element of G here either fixes the pole, that is it either fixes the line and rotates along the line, or it interchanges the. So basically, this operation gives us the dihedral group. So if we have yeah, so if we have the square, so we have here we have two operations. For the cyclic group, we had one operation. So here we have two operations. So for fixing the poles, we have this. We have a line L which passes through the center. So we once again have the unit sphere. We have the line passing through the center, so it rotates along. So we have the four vertices. It rotates along this line L, and then we also have another line which passes perpendicular. We can call this L dash. What is L dash does is, if we take the dihedral group of a square, we know it has 8 operations. So it is identity r square r cube. R is rotations, so each rotation is 90 degrees. So 90 degree. R square is 180-degree rotation, and R cube is a 270-degree rotation. And then we have the symmetries, that is, which flips it along the symmetrical line. So we have one. So if we consider this line to be y, so it flips across y, ry, r square y, and r cube y. So this operation we can, here we have reflection in R2. So when we consider it to be a unit sphere, the same operation can be obtained by rotations through pi. So along this line y, if we flip it, that is basically do a pi rotation, that is 180-degree rotation. We can construct all these eight. So we get the dihedral group and the orbit O3. So we have three orbits. So one is the orbit O3. The other is other orbit is for vertex, and the other is for face. Right, all the one is for the vertices and one is for center of faces. So those are the three orbits. So finally, we have taken the case one, which is we have taken R2 to also be true. Next case, if we take these three triplets are not possible. So this is the final case, basically. So R2 greater than or equal to 4, R3 greater than or equal to 4 is not possible, because if we have that, we'll get equal to 0 or less than 0. Again, if R2 is equal to 3, R3 is not, it is not possible to have R3 greater than or equal to 6. Again, we get negative value. So then we only have these three options, remaining options, which is 2, 3, 3. This is R1, R2, R3. Same for the remaining two. So R1 is 2, R2 is 3, R3 is 3. So if we consider that, we get n is equal to 12. For 2, 3, 4 combination, we get n is equal to 24. For 2, 3, 5 combination, we get n is equal to 60. So we have from the orbit stabilizer theorem, we have capital N is equal to small r times small n. So from each of these, we can obtain, these are index. So that is 12 by 2 gives us 6, 12 by 3 gives us 4, 12 by 3 gives us 4. So if we observe this middle column, The middle column has all three. So each vertex will be connected to three other points in the space. So this is basically gives us the tetrahedron. For this gives us the octahedron, that is this combination. The 24 rotations gives us the octahedron, and the 60 rotation is the dodecahedron. So we have eliminated every other case from our observation. I should probably better say it as tetrahedral group, octahedral group, and icosahedral group, because for octahedral group we have either cube or octahedron, and for icosahedral group we have either dodecahedron or icosahedron. So these are all the classifications possible for finite subgroup of SO3. We are not doing the infinite classification. So for one orbit case is not possible. If we take the two orbit case, we get the cyclic group. If we take the three orbit case, for all the three order of the stabilizers 2, we get the dihedral group, and then for the remaining three cases, we get the tetrahedral group, octahedral group, and dodecahedral group. If we look at their orbits, then this corresponds to their edges. The first term will correspond to the edges. The edges are connected to the two vertices. This number will correspond to vertices, and this will correspond to the faces. So stabilizer, we know that stabilizer has, if we take the dodecahedron, the stabilizer has the term 5, which I discussed in the previous lecture. Do dihedral groups only refer to 2D shapes in a plane? Dihedral group or n-dimensional polygons. So yes, we refer to 2D shapes, but in this we have embedded them into the unit sphere. So we can work in that way too. So I will probably go over this once again very quickly, because this was a pretty long proof. So we defined SO3. Yes. We wanted to claim that for every finite subgroup G of SO3 is only of any one of the 5 forms. It can either be the cyclic group, dihedral group, tetrahedral group, octahedral group, or icosahedral group. So to work with this, we first took a unit sphere, and then we defined that every rotation, every object orientation preserving rotation will pass through a line, and that line will meet the unit sphere at 2 points. We call them as poles. Next, we have that when we have G operating, then it will move only from one pole to another, and these poles are vertices, center of faces, and center of edges. And then we claim that this was a valid action. And then we basically started counting. We first looked at their orbits and their stabilizers. Their stabilizers form a cyclic group, and then we looked at their orbits, which is number of poles. Using orbit stabilizer theorem, we counted and obtained this formula. From this formula, we derived that there can be only 3 orbits. So we went by elimination basis, one by one, case by case. We went and found all the 5 possible subgroups. So any questions related to this topic? The next topic we are going to look at is operating a group on itself. So far, with group operations or group actions, we have taken a group G. and then taken a group S and had the group G operate on S, and the final result will be in the S, the set S. But now we are going to have G operate on itself. So when we have G operate on itself, uh, plays the role of both the group as well as the set. So we have this action, uh, this G cross G. This is the map we have. So, and this is how we denote a group action. So this GX is also in the group G. Before we had this GX belong to the set S. When we have group act on itself, clearly we have that inside the group. So this operation is transitive because Gx belongs to G, so there can only be one orbit since we have the G. So the stabilizer then, since this is transitive, by orbit stabilizer theorem, the stabilizer can only be the identity. When the identity is, when the stabilizer is the identity, the action will be faithful. Faithful in the sense, by definition, uh, it is an injective mapping. So the homomorphism, this is the common map we have. Mg is the permutation. So G and then left operation X. This is the homomorphism. This is injective. So next we have Cayley's theorem. So Cayley's theorem states that every finite group G is isomorphic to a subgroup of symmetric group. So if G has order n, then G is isomorphic to symmetric group Sn. So first we start that group action is faithful when a group acts on itself. So G is isomorphic to the permutation group since it is a faithful action. So permutation map is bijective. We had surjectivity. We previously discussed that permutation map, the homomorphism itself may not be injective. So since now the action is faithful, we have that G is isomorphic. G is isomorphic to permutation map. Now since G has the order n, then the permutation map will be isomorphic to Sn. So this was what we had to claim. So G isomorphic. So this was the claim we had to make. So this simply comes because we have that the action is faithful. If this action is not faithful, then we will not have this Cayley's theorem to be true. But the result we have is not particularly very useful, since if we wanted to count say some finite groups with this, then Sn will have order to be n factorial. So instead of directly using that, we define another result. We take the conjugation operation. So conjugation is, if we take G left action on X, then Gx G inverse will be the conjugation. So under this is a valid group action. I'm not going to verify that here. If we take the stabilizer of the group action now, it has a special name which we call as the centralizer. So centralizer is basically Gx G inverse will give us X. That is basically it is the set of elements in the group with which X can permute. So X can permute. So if it permutes, then we have G inverse X. So then it is X, or the other way. So we call the stabilizer as the centralizer, and orbit we call as the conjugacy class. So if we have conjugacy class, orbit is basically again by definition where the X travels under the action. So far we so it is basically X equivalent to X bar. So this relation basically gives us this. So Gx G inverse is some other element within the same orbit or the conjugacy class here for some group element. So if we have some G satisfying this, uh, uh, we will have some G satisfying this, and it's just all these elements. So conjugacy class or orbits, we saw that as equivalence class partitions the set, orbits will also partition a set. So the uh, conjugacy classes will also partition the set G. So for a if it is not finite, then we will have that G is equal to summation of Ci. If the partition is not finite, we will have this solution. But for a finite set, since we are mostly discussing about finite sets, this partition will also be finite. So if we number this, so by numbering, here we use this notation. So when we number this, the C1 will be for the centralizer. That is basically the identity. This is for the identity. The other can be any other conjugacy class. So this is an example. So the dihedral group has three conjugacy classes. One is the identity. The other is the set of rotations. And the other is the reflection. So D3 has six operations. Identity is one of them. There are two rotation operations and three reflection operations. So we have uh, we can see that the conjugacy class equation is satisfied. So next, from this we can see that and if we take any element x and it belongs to the center of the group G. So this definition is what we typically use for center of the group. Mm, this part of the equation is what we use for the center of the group. Center of the if some group G we have taken is non-abelian, then center of group is all the elements which commute with every other element of the group. So if you have like four elements, then those four elements will commute with all the other elements of the group. So that is the definition of center of a group. So a group X will, an element X will be in the center of the group if and only if the centralizer of that element is the entire group. So if we have some element in there, this basically comes from the definition. That's why we don't have any proof. So when we have it is in the center of the group, then it will commute with every other element. When it commutes with every other element, it will satisfy the centralizer definition. So the centralizer will be the entire group G. So the when it commutes with every other element, if we look at the conjugacy class, uh, x dash will be the element x itself. So the conjugacy class will have only that element. It will have no other element. So I think at this point we can take a 5 minute break. Yeah, we'll meet in 5 more minutes, and we will continue with the next topic, P groups. Uh, till then, I can take any questions. So we'll resume now with our next topic. The next topic we are going to look at is called P group. So the definition is that if a group G, a finite group G, is of a positive power of a prime P, then we will call it as P group. So for example, G can be 2 power 3, 2 power 4, 4 etc. It will be a P group. So what we have is so we have a couple of few propositions related to P groups. So first is that center of a P group G has order greater than 1. Uh, so if the order is is equal to 1, when we have order is equal to 1, so G is of power P power I. So we take the class equation. So the left side is the group order. Here, yeah, here as I have defined, left side is the group order G. So we take P power I. The first class we always take is the center. Center, if we assume that center is only one, that is the identity element, then every other element, the sum of there will be other conjugacy classes. So we take the sum. Uh, so one another thing that we have with conjugacy classes is that since they are essentially orbits, their individual order must divide the overall order. Uh, so if we take this, then we go modulo p. So when we go modulo p, this will become 0. Uh, this entire term will become 0. So we will basically have a plus 0 here. So we have a plus 0 here. But this relation cannot hold. Since 1 mod p will be a 1. It cannot be 0 because p is some prime power. So it can be 2, 3 or something. So this relation cannot hold. So this is false. So the center of G will have order greater than 1. So next proposition is that basically we are generalizing the previous statement. So if G is a P group which operates on some set S, uh, and we assume that the order of G does not divide the order of set. So there is a fixed point action G on S. That is, there is at least one element which uh, such that its stabilizer, that is the centralizer of that element is G. So when we say that the centralizer is G, so we say that this will have the center of this is at least E comma S. It can also be other elements. So we are saying that the center at least has these two elements. So there is at least one such element S. So that is the generalization of the previous statement. So next is that every order of P square is abelian. So this is again a simple proof. So we will take some group element X. So if X is in the center, then it will also be in the centralizer. So we will assume that X is not in the center, but X is one. So if we take the centralizer of X, so there is a difference between both. So keep in mind. So if we take the centralizer, then the centralizer will be strictly greater than the center of the group. Because the centralizer will at least have the whole center along with X. The centralizer Zx will have at least the entire Z plus X. So the order by the conjugacy class relation, their orders must divide P square. So uh, when the order is P square, we only have 3 possible combinations. It can either be 1, P or P square. So in the previous relation, we have claimed that the center of a P group has to be greater than 1. So it cannot be 1. So next relation, Z has to be less than Zx. Z has to be, the center as less than the centralizer of X. So the only possible order for the center of Z is P. Uh, then, since the Zx is greater than P, the only possible order for the Zx is P square. But when Zx is P square, we are claiming that Z of X is the entire group G. So when we claim that, basically means that X actually does belong to the center. So our initial assumption here was wrong. This assumption was incorrect. So this is the claim we are making. So next is that a follow-up for that. This proposition is that every group of order P square is of two types. It is either a cyclic group of order P square or it is product of two cyclic groups of order P. So the first one is very simple. if a group is of order p square, then it has either two element of order p or order p square. So when there is an element of order p square, then it will generate the entire group. So this proves one. If the group is of order elements are of order p, then apart from the identity element, every other element will be of order p. So we will take two elements x and y. Uh, we assume that x generates a subgroup h1 and y generates h2, and that y does not belong to the y is not generated by x, so y does not belong to h1. So when we take that, their intersection will only give us the identity, and then since G p square, the G is abelian since because it is of order p square. These groups are normal. So if we take their product must be strictly greater than h1 and h2 because when we take their product, uh, so if we consider H1, H2, it has both elements from H1 as well as H2, and it can at most be P square. So their order must divide P square. So H1, H2, their product is isomorphic to G. So it is a product of two cyclic groups of order P. So this is the final topic of today's lecture, which is the class equation of the icosahedral group. So if we take the class equation of, we saw that class equation is given by this relation. So icosahedral group has 60 rotations. So it has icosahedral group is 60 rotations of either a dodecahedron or an icosahedron. So dodecahedron will have 12 faces, 20 vertices, and 30 edges for a dodecahedron. An icosahedron will have 20 faces, 12 vertices, and 30 edges. Since we covered dodecahedron in detail in the previous lecture, this lecture will focus on icosahedron, but the rotations remain the same. So first we will look at the possible operations of an icosahedron. So before that, I want to, yeah, we will look at rotations of icosahedron. So this is one vertex here. So we can see that at the top, if we take the top point x, we have 2 pi by 5 rotations. So if we consider this position to be the identity, then the next position will be 2 pi by 5, 4 pi by 5, 6 pi by 5, and 8 pi by 5. So we get 2 pi by 5 is the minimum rotations for vertices V. If we take the faces, this forms one face. If we take the pole of the vertex goes through this line, straight line. So as I said, I wanted to originally show that a pole can be shared by two different actions. So this is basically shows this. The line goes through two lines. So yeah, that I wanted to show this. And then next, if we take the face, we have a line going through the space to the center. This space will have a 2 pi by 3 rotation. So we have identity, 120-degree rotation, and then 240-degree rotation. So 2 pi by 3 is the minimum rotations for the face. And then if we take any edge, we only have a pi rotation. We have identity and the pi for the edges. So each face will go through a 2 pi by 3 or a 4 pi by 3 rotations excluding identity. So now we want to count the number of rotations. So we have established that the group G, which is order preserving, has 60 rotations. So we want to count all the rotations. So for 60 rotations, we have faces, vertices, edges, and the identity. So if we take the faces, each face can go to. So if you take this face, it can go through a 2 pi by 3 or a 4 pi by 3 rotation. So we have 40 rotations. But if we take consider this, each uh, pole, each line goes to two poles. So it also goes to the opposite phase. So we have made a double count. So we'll have to divide by 2. So we have 20 to 240 rotations. So these are two rotations, 20 phases, so 20 to 240. If we divide by 2, we get 20 rotations since we have double counted. If we take each vertex, we said that along with the identity, we have 5 rotations. Excluding identity, we have 4 rotations. 2 pi by 5, 4 pi by 5, 6 pi by 5, 8 pi by 5. So again, we are double counting because a vertex will go through two lines. So if we take these 2 points, that will be going through these two lines. So we are double counting. So 12, there are 12 vertex. So 5 on the top surface, there's one top point, 5 on the bottom, and the bottom point. So there are 12 vertex. There are more. 12 vertex. 12 into 4 because we have 4 rotations and then we are doubly counting. So we have 24 rotations for the vertex. If we take each edge, we have a pi rotation, and then since again if we take the a line going through the center of the pi, this line will also go to the opposite side, so we are doubly counting the number of rotations again. So we have 30 into half, which is 15 rotations. So if we add all of them, so we have an identity, we have the identity position for the entire icosahedron, so that gives us 1. We have 15 rotations from the edges. We have 24 rotations from the vertices and 20 rotations from the faces. If we add all of them, we get a 60 rotations. But this is not a class equation. If we go to the definition, the class equation is for conjugacy classes. So we have all these. We have to split them into orbits on each conjugacy class. So if we go and split them into orbits, we see that identity is conjugate to itself. So identity is fine. Next is rotation of edges. So each 180-degree rotation will also be conjugate to itself. So that is fine. Next we see that phase, we have 2 rotations, 2 pi by 3 and 4 pi by 3. So 4 pi by 3 is, we can also rewrite this as minus 2 pi by 3. So this is conjugate to itself. So all the phase rotations are conjugate. And then if we take vertex rotations, they are into two classes. So vertex, we had 4 rotations. So we had 4 of them. So these two form an orbit, and this middle one form another orbit. So we get 2 orbits if we take vertex. So this one will form. We have total of 24 rotations. So if these form one orbit, these form one orbit. So we have 12 rotations in this orbit. That is 2 pi by 5, and 12 rotations for 4 pi by 5. So 24 is split into 12, and then there are no other orbits. So these are all the orbits, all the conjugacy classes. So this is the class equation for an icosahedron. That is the group I, which we also discussed in the section 5.9. That is when we found the finite classification. So this is the class equation. So these are all the possible equations, and we have also defined how they will rotate. So these are all the possible rotations for the class equation. So next we have 2 small rules. So first we have a definition. So a group is called a simple group if it is not a trivial group. So G should not be the identity. And G contains no other proper normal subgroup. So if we remember, G always contains 2 normal subgroups, which is the identity. So if I consider it as capital E, so G will always have E and G itself to be normal to this. These 2 groups will always be normal, but we have to look only at the proper subgroup. So if there are no proper subgroups, proper normal subgroups, then we call that group as simple group. For example, cyclic group of prime orders. So we take F7, then that will be a simple group. So that is one example. So we have uh, the icosahedral group has no proper normal subgroup. So we are basically calling icosahedral group to be simple. Uh, we are basically claiming that the icosahedral group is a simple group. So for proving this, we use two lemmas, which are basically that if a normal subgroup contains some element x, uh, then it contains the conjugacy classes, and these conjugacy classes, this is formed by multiple. So the sum of conjugacy classes. I should basically say here it is sum of conjugacy classes, not just conjugacy classes. So it is sum of conjugacy classes of Cx. So it will always contain the identity class, and then there will be other classes. So if then the order is preserved. So basically, order of the subgroup, normal subgroup is the order of the sum of conjugacy classes. So if we look at the class equation of the icosahedral, if we add any two of these elements, then we can no longer uh, divide the class equation. So by the orbit stabilizer theorem, this must divide the order. So, but if we add them, it will no longer divide the order. So, since it will not, we will not. No combination gives us a proper divisor. We will see that it has no proper normal subgroup. So another one is that the icosahedral group is isomorphic to the alternating group A5. So assume icosahedral group also has a dodecahedron. So we will assume that there are 5 cubes uh, inscribed in the dodecahedron. So if I operates on 5 cubes, then I we will have a homomorphism from I to symmetric group S5. So if we take the kernel of a normal subgroup, the kernel is either E or I, but if the kernel is the entire group itself, then we'll call it as a trivial operation. But this map is not a trivial operation. So if we have an dodecahedron, if you have a dodecahedron here, so we'll basically have a cube inscribed in this dodecahedron. So if you have a cube inscribed in this dodecahedron, there are actually five. So 5 of them. So if we do operations, these are not trivial operations. So that is basically what I want to claim here. These operations are not trivial. So the kernel can only be the identity. It is only the identity. So when we go from I to S5, we already established that surjectivity is basically given. So since the kernel has only the identity, we have injectivity. So this homomorphism we have is actually an isomorphism when going from the icosahedral group to the permutations. So we will now go from we will now look at if we go from S5 to image of S5 to we consider we will take another homomorphism psi, which is basically the sign homomorphism. So it has a +1 or -1. So we will have a map from I going going to S5 to 5. This is the permutation, the symmetric group, and then this will go to a sign homomorphism. So if this map is surjective, uh, if the psi is surjective, then the order of the image is 2. Here the order is 60. So by Lagrange theorem, we see that if 60 is equal to 2, here we have the order of the kernel, then the order of the kernel will be 30. This is not possible because we saw that if the order is 30, then the icosahedral group I is no longer a simple group. It is a compound group, but I is a simple group. So order is not 30. So uh, here we only have I is only the trivial. So the minus one is not there. It has only the plus one. So when we have only the plus one, then we have the trivial map. So it is no longer the surject. It is this map is not a surjective map. So we basically say that the image is contained in the alternative group. So we only have the plus one. So it is contained in the alternative group. Since this is also isomorphic. Um, Map is contained. So this map is contained. So we have an isomorphism between I and A5. If we had the order of the symmetric group is 120. Uh, 1, 0. The alternative group A5 will have order 60. So since the map only goes to the trivial element plus 1, uh, I is isomorphic to A5. So that is what we wanted to establish here. So yeah, I have actually covered everything I wanted to cover in this lecture. So if I do a quick recap, we covered uh, all we did the finite classification of SO3. We took quite a while. Uh, we first established that by calculating the number of poles, we established that the maximum number of orbit can be 3. Then we went case by case basis to establish all the 5 classifications. So next we looked at the Cayley theorem, and then we looked at class equation, another important concept. Class equation. We then looked at P groups, and then we finally looked at the class equation of icosahedral group. So